Hello everyone. So today I'm going to be looking at the 2015 AP Physics 1 free response question number 1, the problem with the pulley system. So the question is, two blocks are connected by a string of negligible mass that passes over massless pulleys that turn with negligible friction as shown in the figure above. The mass M2 of block 2 is greater than the mass M1 of block 1. The blocks are released from rest. Part A. The dots below represent the two blocks. Draw free body diagrams showing and labeling the forces, not components, exerted on each block. Draw the relative lengths of all vectors to reflect the relative magnitudes of all the forces. So, for the forces on block 1 here, we know that the pulley system is going to be traveling this way because they told us in the problem that the mass of block 2 is greater than the mass of block 1. So the tension force pulling up on block 1 because of the rope will be greater than the gravitational force pulling down on block 1. So we should have a longer arrow for the tension force than we do for the gravitational force. Now for block 2, on the other hand, the pulley system is going in that direction. So the gravitational force pulling down on block 2 will be greater than the tension force pulling up on block 2, so that the pulley system can travel in that direction. So we will have a longer vector arrow for the gravitational force than we do on the tension force. Now, as always, air resistance is negligible, and it said massless pulleys with negligible friction. So these are the only forces that we have to worry about here. There's no surfaces, so we don't have to worry about a normal force. No friction or anything. Alright, so part B says derive the magnitude of the acceleration of block 2. Express your answers in terms of M1, M2, and G. So I'd like to show you a couple ways of doing this. So the first method is sort of almost like a shortcut method that basically uses Newton's second law, A equals sigma F over M. So for this method, what you need to do is you need to figure out what the net external force acting on the system is, and then divide it by the total mass of the system. So in this case, we know that the net force acting on the system is going to be the gravitational force acting on block 2 and the gravitational force acting on block 1. And since they are opposing forces, we're going to have M2G, the gravitational force acting on block 2, minus the gravitational force acting on block 1, over the total mass of the system, which is going to be the mass of block 1, which is M1, plus the mass of block 2, which is M2, over M1 plus M2. So there's your answer for the first part. Now, the second method is definitely the most common method that you'll see out there. And that involves setting your coordinate system and actually going through all of the separate forces, finding tension forces, and then setting the tension forces equal to each other. So let me draw another picture here. We've got the table, got a couple of pulleys here. We've got the string, got block of mass 1, got the larger block of mass 2. So oftentimes doing this method, what you'll see happen is you'll see an interesting setup for the coordinate system. Because, you know, this one is traveling this way. You have the acceleration is negative. But if you use conventional coordinate systems, the acceleration for this one has the same magnitude, but is positive. So oftentimes what you'll see done is for this block here, you'll see down made positive and up made negative. And for the other block, you'll see up be positive and down be negative. And you need to be really, really careful if you do decide to do it this way. Because that if you make one mistake saying this force is negative instead of positive, or positive instead of negative, then it throws off your whole entire answer. So the first thing you start with is defining the net force on block 2. So going with this coordinate system, we know that sigma F on block 2 is equal to the sum of all the forces. So that's going to be Fg plus Ft, where Fg is the gravitational force and Ft is the tension force acting on the block. And we know that the net force acting on this block is going to be the mass times the acceleration in accordance with Newton's second law. And since we define downwards direction as positive, we know that this is going to be mass of block 2 times positive acceleration. So this is going to be a positive force is equal to the force of gravity, which is also going to be positive in this case because it's acting downwards. So we have m2g minus the magnitude of the tension force because we set upwards as the negative direction. So what we want to do is we want to isolate the tension force. So we add tension force to each side and then subtract m2a, and we get that the tension force acting on block 2 is equal to m2g minus m2a. So that is the second block. Now if we look at the first block in this case, we've set the positive direction as upwards, and we know that the net force is going to pull it upwards. So sigma F1 is equal to, in this case, however, the gravitational force is going to be negative, because in this direction, the downwards direction, is negative in this case, and the gravitational force pulls it down. So we're going to have negative magnitude of the gravitational force plus the magnitude of the tension force. So what this tells us is that m1a is equal to the tension force, sorry, almost wrote plus there, minus m1g. So what we're going to do is we're going to add m1g to each side, and we get that the tension force acting on the first block is equal to m1a plus m1g. So now, what we know is since there's no mass of the pulley or string, and there's no friction on the pulleys, the tension force throughout this string is going to be the same. Meaning the tension force acting on the second block is going to be equal to the tension force acting on the first block. So what we can do is we can say Ft2 is equal to Ft1. And then from there, we just set our expressions equal to each other. So we know that Ft2 is equal to m2g minus m2a. We're going to set that equal to Ft1, which is m1a plus m1g. So we're trying to solve for the acceleration of the block. So what we need to do to figure out the acceleration is isolate the acceleration on one side. So how I'm going to do that is add m2a to each side, and then subtract m1g. So what that gives us is m2g minus m1g is equal to m1a plus m2a. Now what we can do is we can factor out the a, and we end up with m2g minus m1g is equal to a times m1 plus m2. Then divide each side by m1 plus m2. Then we get our answer. The acceleration is equal to m2. If you want to, you can factor out the g as well up here. So I'm going to do that. We have m2 minus m1 g over m1 plus m2. And that is the same result we got for the other one, as long as I didn't screw up the 1 and the 2, which I will do sometimes. Let me just check to make sure. Yeah, that's right. Now, the third method is a method that you probably won't see very often at all. This one deals with conservation of energy. This one's a little more convoluted, a little less practical to use, but it's still fun to do. So, what I'm going to do here is I'm going to draw another diagram with our block 2, going to make the table a little bigger in this one, and our block 1. So we know that this height here, let's say this is h2 naught, and this is h1 naught, and we know after it travels a little bit, let's say this distance, we'll set this is h2. We know this one will go up, so we'll set this as h1. Now how we want to set this up is we know the energy at the beginning of the problem is we've got our potential energy of block 2, u2 naught, plus our potential energy of block 1, u1 naught, is equal to, now since there's no dissipative forces, we know that all of that potential energy is going to go into kinetic energy eventually, because there's no friction and there's no air resistance. So we know that this is going to equal u2 plus u1, where u2 and u1 are the potential energies where we would like to analyze the motion. Like, for example, after it's gone down this far, it still has gravitational potential energy, but it also has kinetic energy. So we have K1 plus K2 as well on this side. So now we know the equation for potential energy is mgy. So in this case, for potential energy 2, it's going to be mg, and we said its initial y position is h2 naught. So we're going to say h2 naught plus, oh, forgot the 2 there. Make sure to separate the masses too, because they're not the same. Plus m1 times g multiplied by, we said the initial height here was h1 naught. So h1 naught is equal to, and now where we're looking at it, we know we have our potential energy is going to be m2g times h2 plus m1g h1, where h1 and h2 are the heights of block 1 and block 2 at the position where we're analyzing the motion. Plus, we also have some kinetic energy. So the kinetic energy of block 1 is going to be 1/2 of mass 1 times the speed squared, and we're going to add on the kinetic energy of block 2 as well. So we have 1/2 times the mass of block 2 times the speed squared. So now what we'd like to do is isolate the velocities. You'll see why in a little bit. So what I'm going to do is I'm going to subtract m2g h2 and m1g h1 from each side. Put all the potential energies on the same side. So what we end up with is m2g, oh whoops, it should be h right there, h2 naught minus h2 plus m1g times h1 naught minus h1 is equal to, and now we can factor out the velocity on this side. So we have 1/2 times m1 plus m2 multiplied by v squared. So this is where the velocity squared comes in, why we wanted to isolate the velocity. Because if you remember from kinematics, one of the equations, v squared is equal to v naught squared plus 2a, and in our case, it's going to be, oh, whoops. Sorry, messed up the setup a little bit. Shoot. There we go, that's better. We're going to have plus 2a times delta h, because I decided to use h instead of y for this problem. So we know that the v naught is 0, and v squared is right here. So we know that v squared is equal to 2a delta h. So now, I'd like to just jump back down here for a second. So we know that the change in height is going to be height final minus height initial, pretty much. In this case, we have the height initial minus height final. So what I'm going to do is I'm going to bring a negative out front. So we have negative m2g, and this is going to give us h2 minus h2 naught. And I'm going to do the same thing over here, minus m1g. And we have h1 minus h1 naught is equal to 1/2 times m1 plus m2, now multiplied by 2a delta h, because we subbed that in for v squared. Now the 2 and the 1/2 will cancel out, leaving you with m1 plus m2 times a delta h. Now come back over to this side, we have negative m2g, and now since this one goes down, its value for delta h is going to be negative. So I'm going to write a negative quantity delta h, because it's going downwards. So these negatives will cancel out. Now for the next one, it actually goes up, so it has a positive change in height. So we have minus m1g plus delta h is equal to m1 plus m2 a delta h. Now I factored that out is because the change in height of each block, since they're tied together, is going to be the same. So we know that, let's say this is delta h1 here, and this is delta h2. We know that delta h1 is going to be equal to delta h2. So this delta h here is going to be equal to this delta h here. So what we can do is we can factor out the m1g and the m2g and have just delta h. So that's going to give us m2g minus m1g delta h is equal to m1 plus m2 a delta h. Now once again, we're trying to solve for the acceleration of the system. So how we're going to do that is by dividing by m1 plus m2 times delta h on both sides. Now as you can see, the delta h's here cancel, and that gives us a is just equal to m2g minus m1g over m1 plus m2. And there we go. That's 3 different methods for solving for the acceleration of the system. Alright, now let's move on to part C. Indicate whether the magnitude of the acceleration of block 2 is now larger, smaller, or the same as in the original 2-block system if a block of m3 is added to the system. So they also tell us that there's no friction between block 3 and the table. And it says, is the acceleration going to be the same? Explain how you arrived at your answer. So for this one, let's take a look back at method 1. So we saw that the acceleration is equal to the sum of the external forces acting on it over the mass of the system. So if you look at this, the external forces acting on the system are still the gravitational force acting on mass 1 and the gravitational force acting on mass 2. So the net external force is going to be the same. So sigma F is the same. But throwing in the block 3 with a mass of M3 changes the total mass of the system. So what we had last time was A is equal to M2 minus M1 G for the force. That is going to stay the same, because block 3 doesn't apply any sort of external force. Now there's internal forces with like the tension forces, but those aren't going to change the acceleration in this case. But if we look at the total mass of the system, where in part 1 we had just the 2 blocks, and we had over M1 plus M2, in this case we have M1, M2, and M3. So this is going to give us M1 plus M2 plus M3 for the acceleration. And by throwing another mass on the denominator, we are decreasing the acceleration of the system, because making the denominator bigger is going to make our answer smaller. So the magnitude of the acceleration is actually smaller. And that is the 2015 AP Physics 1 free response question number 1, the one dealing with a pulley system. Thank you everybody for watching, and have a good rest of your day.